Test number 7. Good luck, everybody. We'll start with number 38, i.e. number 3. A uniform electric field exists in a region, and then a neutral conducting spherical shell with a stationary charge of plus 2q at the center is placed in the region, as shown above or below. The radius of the spheres r. The flux through the sphere depends on the value of. Good question. That's Gauss's law. Paging Mr. Gauss. Closed integral EdA is equal to q over epsilon naught. So that means the answer obviously has to be E. The only thing the flux cares about is Q. That equation on the left, integral EdA, that is your integral for the flux. What is the flux? Again, think of it as counting up all those electric field lines through that surface. Two ways to have a really big flux: have a really strong electric field or have a really big area. Two ways to fill up your rain bucket: have a really strong rainstorm or have a really wide mouth to your rain bucket. One way to decrease the area is to hold your rain bucket at a strange angle, not perpendicular to the direction of the falling rain. The sphere is super awesome as a Gaussian surface because those lines are perpendicular to the surface of the sphere. Those electric field lines are perpendicular to the surface of the sphere. On the left, we have a big sphere, so we have a bigger area and a weaker electric field. On the right, we have a smaller sphere, a smaller area, but a stronger electric field. They cancel out. It does not depend on R. The most common answer that I received was answer D, but answer E is correct. It does not depend on R. Flux is equal to Q over epsilon naught, just the Q inside. And someone's thinking about, what about E? E is an external electric field. Those field lines, the number of field lines that go into the sphere equal the number of field lines that go out of the sphere. You only care about an enclosed charge. Q enclosed over epsilon naught. Number 52, i.e. number 17, a battery with EMF epsilon and internal resistance 30 ohms is being recharged by connecting it to an outlet with a potential difference of 120 volts as shown there. While it is being recharged, 3 amps flows through the battery. Determine the EMF of the battery. We'll be using Ohm's law. I equals delta V over R. That's how it appears on the equation sheet. I like V equals IR. 120 minus epsilon is equal to 30 times 3. And we're trying to find EMF epsilon, and the answer there is 30 volts. Now, the most common answer I received was A, 210 volts. And you see what happened. That would be true if you turn that battery around, but this battery is being recharged. Notice how those two batteries are pushing charge in opposite directions. One of them is a, hey, let's go counterclockwise type of battery. The other one's a, hey, let's go clockwise type of battery. So watch it. Number 63, i.e. 28, a parallel plate capacitor with a dielectric material between the plates with a constant K. Not kappa this time, but K. The capacitor is connected to a variable resistor R and a power supply of potential difference V. Each plate of the capacitor has a cross-sectional area A, and the plates are separated by a distance D. Which of the following changes could increase, okay, we got to write this down, increase the capacitance, increase C, and decrease Q. Increasing C and decrease, that's kind of strange. You're increasing the size of your suitcase and decreasing the number of socks in your suitcase. So let's take a look at some equations. No, let's start by crossing off these options. Why? They all had to do with changing R. We don't care about you, variable resistor guy. Why? Because when the capacitor is fully charged, the current goes to 0. When the capacitor is fully charged, the current goes to 0, so there's no voltage drop across that resistor. So we don't care about the resistor. If the resistor is bigger, it's going to take longer to charge that capacitor. But we got time. We can wait. We don't care about R because I goes to 0 when the capacitor is fully charged. Now we can bring in our equation. Capacitance is equal to kappa epsilon naught A over D. Makes sense. The bigger A is, the bigger the area of the plates, the more charge you can fit on there. The bigger the capacitance, the bigger the size of the suitcase. A positive charge on that positive plate is going to like a small d, so we can see the negative charges across the distance. A positive charge on the positive plate is also going to like a kappa, gonna like a dielectric material that's going to orient itself in the electric field. This is all indicated on the lecture notes, but is no help to us because here B and D seem to both be good. We are decreasing D. A smaller D will give you a bigger C. Increasing K will give you a bigger C. Also, what about Q? Well, Q over C is equal to V. That's the definition of capacitance. What will give you a decreased Q? Well, a decreased V. I bet you'll see a capacitor. I know you'll see Gauss. I bet you'll see Gauss's law. I don't want to say no. I bet you'll see Gauss's law. I bet you'll see a circuit. I bet you'll see a capacitor of some sort. Anyway, number 68. This one is your official kick in the head. Otherwise known as number 33, a spherical charge distribution varies with radius r by the equation rho equals AR, where rho is the volume charge density and A is a positive constant. The distribution goes out to a radius r. Which of the following is true of the electric field strength due to this charge distribution at distance r from the center? Yikes. Help. What is a volume charge? This is a volume charge density. Rho is equal to Q over V, or as I prefer to think of it, Q is equal to rho V, because if rho changes like ours does, we could say that the total Q is equal to integral rho dV. Did you hear me? Q is equal to integral from 0 to capital R of rho dV. Q is equal to integral from 0 to R of AR. That's what rho is equal to AR dV. But what is dV? Well, dV is equal to a small little piece of volume. It's equal to 4 pi r squared dr. It's equal to a small little piece of volume. It's equal to one of these shells. This is the onion method. We used this in class a million years ago. This is the onion method. Think about each of those onion shell things. They all have a volume. They have an area of 4 pi r squared and a thickness of dr. They have a small little volume of 4 pi r squared dr. Just go with it. Let's take those things and integrate. And now we can take Q is equal to 4 pi A, integral from 0 to R of R cubed dr. You see, we put the two things together, and we can do. Can you do this integral? I'll wait for you. Could you do that integral? I hope you could do that anyway. So, and that is an answer to a question nobody asked. That's just our warm-up to answering this question again. That's our answer to the question, what's the total charge on this sphere? A question nobody asked. Again, what are we trying to find? We're trying to say which of the following is true of the electric field strength due to this charge distribution at a distance r from the center. And we know the total charge on the... Wait a minute, so how do I find the electric field? Once again, we're going to Gauss. And the good news is you can use Gauss's law. Closed integral EdA is equal to Q over epsilon naught. Closed integral EdA is equal to Q over epsilon naught, which means the flux, the area times the electric field. I told you to think about that spherical surface. That's an awesome surface to use for a point charge because the electric field lines are perpendicular to the surface of the sphere at every point. Anyway, 4 pi r squared times the electric field is equal to Q enclosed over epsilon naught. And the good news is we already figured out an expression for the Q enclosed. It's equal to 4 pi a small r to the fourth. That's the Q enclosed. See what we did there? That warm-up problem, finding the total charge on the sphere, that's the same method we use to find the charge inside any small r radius sphere inside this distribution. And I'm getting a little bit dizzy here, so let's just divide out and solve for the electric field strength is equal to AR squared over epsilon naught. And that means the answer is E. The electric field increases non-linearly for r is less than capital R. And did they really expect you to go through all those steps? I don't think so. I think they expected you to remember this. This is the electric field strength inside a spherical insulator with constant charge density. Again, inside a spherical insulator of constant charge density, notice that the electric field increases inside the insulating sphere, and then you got the inverse square law outside of it. Again, insulator, and this is a conductor. Another thing I would definitely think you'll probably run into is this idea of the electric field inside a conductor is zero. So I'm going to say that 2 more times. The electric field inside a conductor is zero. The electric field inside a conductor is zero. Last one, 69, also known as number 34, when a positive charged rod is brought near but does not touch the initial neutral electroscope shown above, its leaves repel. Number 1. When the electroscope is then touched with a finger, the leaves hang vertically. Next, when the finger is finally removed from the rod, the leaves repel again. Well, what's going on here? Well, number one, we have charge by induction. That neutral electroscope is still neutral. 3 negative charges, 3 positive charges. The negative charges are attracted to the rod. The positive charges are repelled by the rod. That's why they make the leaves stand up. This is an electroscope. If you need to research that in your textbook or some other place, an electroscope, then you touch the electroscope. What's happening there? Well, the positive charges don't like it. The positive charges don't like being near that positively charged rod, so they run up the arm. The positive charges run up the arm, and that means the electroscope has now an overall negative charge. I think that's neat. That's called charging by grounding. And as you see with this method, we can give the electroscope a negative charge by a positive charge being close to it and by touching it. Great. So, what's the answer? Well, we can read through those options and right away say no. Protons are not moving. Protons are big and heavy and bound in the nucleus, and they're not moving. The electrons are moving. But I thought you said the positive charge is left. Oh yeah, I said the positive charge is left because that's easier for me to think about that way, but we'll get to that in a second. Are electrons going from the finger into the rod? What about E? No, can't be E. The finger never touches the charged rod. The finger only touches the electroscope. So what does the answer have to be? The answer has to be B. Most common answer was A, but electrons are not going from the electroscope to the finger. Electrons are negatively charged. You could say that electron holes are going missing, like ghost electrons, negative electrons, whatever you want to call it. You could say that electrons are doing the opposite of going from the electroscope onto the hand. Electrons are going from the hand onto the electroscope. Negative charges moving, in this case, right to left, is the same as positive charges moving left to right, because, hey, they're invisible anyway. Again, if you got a suggestion or a request for what we should do next week, let me know, and good luck.